Okay, thank you, Nikki. Hello, everyone. So I'm Ludo Enault, working in the Power HPC team in Montpellier. So for Europe mainly, but we have also a worldwide scope. If it plays is better. So I just put a map to show where we are and where you are. So it's not that far. Yeah, we are the European center for most of the systems stuff in IBM, and in particular the HPC part. Some major achievement to show our scope of work. So the two of the major supercomputer based on Power9 plus V100 has been installed by my team. So Marconi 100. Its specificity is that it's running a similar stack as yours, so Slurm and OpenMPI. We'll come back to that. And Pangea 3, which is running the full IBM stack, let's say. But we are also doing a lot of application work, and I will show an example of what we have been doing with the application team to develop and optimize application on the cluster. So before going to the topic, we are not. I am not 100% aware of what Bede is used to. From what I've been seeing on the cluster, it's mostly AI jobs that are running. So this will cover the HPC use, but it's also to understand the characteristic of the machine. And it's more an introduction. The purpose is really to start the discussion. And as mentioned, Nikki, there will be a third session after covering the, let's say, the basic principles of HPC, how to bind applications, the specific stuff of the machine. We can go in more details in what concern you have with the system, you might have with the system. Usually there is always some. And yeah, then we can cover more deeply what to help you getting more from the system. But it does not prevent you to ask question during this presentation or at the end. So feel free to interrupt. So quickly, so we are on the same baseline. The N8 Bede cluster is based on Power9 systems. So 32 what I would call compute nodes, the GPU nodes that are running V100, so very powerful GPUs with NVLink 2.0. We will come back to it. And for inference nodes, I'm not too familiar with AI stuff, so I will not cover that deeply. Only to mention that the Tesla T4 is optimized for inference versus the V100. So it makes it more efficient. And there is a lot less, from my understanding, in inference, there is a lot less need for bandwidth between the CPU and the GPU. So that's what makes this system more efficient for inference. So my topic will focus on what I call the compute nodes, or the GPU nodes. So quickly, to give you first overview of the base building block. So it's a 2 Power9 CPU, 4 GPUs. The system is designed for bandwidth. So the Power CPUs are not meant to compute too much. I'll come back to it, but the purpose is really to offload everything on the GPU. And the beauty of the system is, thanks to NVLink 2, we have first huge bandwidth available to transfer data between Power9 and NVIDIA GPUs, but we also have a memory currency that helps a lot speeding small work and data migration. And there is a specificity that I will start to mention about. I will come back to it. The PCI Gen 4 adapter for Infiniband. It is shared between Power9 and the two Power9 CPUs. So it's a specific for this system. So it means that both CPU can access directly the network. And we'll see later that it has a big importance. So this chart is really a big overview of the Power9. So it's based on, it's between 19 and 24 cores. 16, sorry. I missed this one for you. We can do 4 thread per core versus Intel, which is 2, but it's not hyper-threading. It's simultaneous multi-threading, which is a little bit better from all the tests we've made. And there is also a numbering stuff that you must be aware of because it's there is a big difference between x86 and Power on that side. Yeah, big DDR memory bandwidth per socket. And the memory hierarchy for the cache is what we call NUCA, non-uniform cache architecture. So compared to x86, where the L3 cache is shared between all the core of the CPU, in Power, it's a private, semi-private cache. So there are dedicated zone of cache for each CPU, but the user can access some part of the memory for some constraint. But by default, you have your dedicated cache. So there is an advantage when you scale in terms of number of core, because on x86 you will have all the L3 cache available. So you will have about, I think it's 24 megabytes available for a single core if you use a single core. But as soon as you go and start using 2 core, you will divide by 2 the available cache. But on Power, you will always have the same level of cache available. So that's a big difference, and it's important to use as much physical core as you can to leverage the cache, the L3 cache, and it's scaling a little bit better than x86. Something that you won't be concerned with at the beginning is the accelerator support, on-chip accelerator support. So the JZip compression. So there is a compression and cryptographic unit, hardware units within the chip. There are 2 chiplets per CPU that are doing that. And it allows to get a lot more bandwidth when we do compression. I say that it does not concern you for now because it requires that 8 update 3 at least to get the full support. So that's something that might be interesting in the future. And I will show you that for Total, we had the same concern regarding that compression units. So regarding the bandwidth, because as I said, it's really all about bandwidth, the architecture of the system. So we have NVLink between Power9 cores and the 2 GPUs, 3 brinks as it's called. So between one Power9 and its 2 GPU, we have about 300 gigabytes per second, 150 per GPUs. Between the GPUs, you have also 150 gigabytes available. And on the memory side, we have about 135 gigabytes per second per socket. And for the PCI Express, so it's Gen 4, it's about 12.5 gigabytes, which is about the same rate as a single EDR link. So you have a full access to the memory, to the network bandwidth of the system. Something that might sound a little bit weak is the XBus of only, let's say, 64 gigabytes. But the purpose, as we'll discuss later, is to really use one Power9 and its 2 GPUs, and on the other side, the other Power9 and its 2 GPUs. So again, it's marketing stuff. I put that because it might interest you. It's all about bandwidth. So the 25 gigabit link are used either for CAPI or NVIDIA GPUs. So if you have an application that can leverage FPGAs, it can be added in the system and provide a lot of capability compared to other systems. Only for reference, it's more that you have the tool and the available bandwidth between and latency between each level of cache. It has no big interest for now, but when you start optimizing application, it's important to have this data. So that's why I put this chart here. And same for the compute unit. So we'll come back to it, but there is no AVX 512. The compute unit is only limited, let's say, to 128 bytes, which might sound low, but again, the purpose of the system is to differentiate serial parts that would run on the fast CPU and the parallel stuff that would run on the GPUs. That is really the purpose of the system. So as a comparison, so Power 8 as well, we don't care too much, but Power 9 and Skylake and the next generation, Skylake, Ice Lake, Cascade Lake, they are sticking to 512 byte SIMD units because there are two main reasons for that. Because it's getting complicated to do more, and the other part is the system is starting to be driven by cloud, and to be efficient in moving to a new generation of system processor, it's better to have a similar compute unit, but enhanced. So that's why everything that Intel or AMD will be doing would be to optimize the instruction per cycle of the CPU, like Power has been doing since Power 5 generation. So everything is mostly driven by cloud now, unfortunately. So a big difference with SMT compared to hyper-threading on x86. So it's really hard-coded, and it's designed to run multiple threads. We have higher frequencies than Intel CPUs or AMD CPUs. So there can be a lot of lost cycle. So the SMT mode allow to run more threads and benefit from the last cycle of some process. One beauty of the SMT is that it does not require a system to reboot to change the mode. But even that, actually, you don't need to be too concerned about that. Only a few applications would benefit from moving from SMT4 to SMT, disabling SMT, just because you can benefit from all today's application. You get a huge benefit to have idle hardware threads to run some MPI communication or underlying copy or whatever. So it's always a good idea to keep the system with SMT4. And usually what we do for all applications is we run a single process or thread context per physical core, and all the extra threads will benefit from two applications that are external to from computation, sorry, that are external from the application. So communication, IO stuff, and everything. So since it's keeping everything in context, we gain a lot in latency in that regard. One key difference between x86 and Power is the numbering. So whatever the state of the system, a given CPU ID will be always the same. So if we turn off SMT, the numbering will be 04. If we move to SMT2, we'll have 01 that will represent the 2 hardware thread on the first core, then 45 on the second core, and so on. So when you move to SMT4, you have exactly the same numbering scheme. So we find it more easier to use in application, especially when you do binding with OpenMP. You can use the keyword and the stride to bind to the appropriate hardware threads. So again, this chart is it's a little bit marketing, but I leave it because it gives some good idea of the benefit of GPU on the Power9 systems, but we'll come back into that in more detail later. So the key difference again is with the Power9 NVLink 2 V100 system is that you have address support for flat address space. So it allows a lot of capability. There is one issue that we have to keep in mind, and which can cause trouble, and that will come back later. But once we know this difference, it's easy to use. So there is high bandwidth, so 65 gigabytes in each direction, CPU to GPU and GPU to CPU. That allows to do a lot of optimization and data management overlapping with computation. So here we see a scheme of the IC922 systems. So at the top we have the four, so the 6 compute units, let's say. So 4 GPUs, 2 CPUs, and at the bottom we see the memory. So we have, in this example, 256 gigabyte of memory on each CPU, and then 16 gigabyte of memory on each GPU. I should have updated with the 32 gigabyte you have. But all this memory can be accessed from either CPU or GPU. So there are some good points, but if you don't pay attention, it can cause trouble. So typically, the trouble can happen here. So when you run the HW lock LS to see the topology, you see that you have machine with a total of 633 gigabyte of memory. So 252, 56 on NUMA node 0, 256 on NUMA node 8, which correspond to the 2 Power9 CPUs. And you have also 32 gigabytes on NUMA node 252, 253, 254, and 255. I know it, but it's hard to really identify. It's the memories that is located on the GPUs. So it means that even from a script, you could use memory on the GPU. So it's good because you can leverage the high bandwidth available on the HBM. But the drawback is that if you don't pay attention, you can you can use memory on the GPU when you don't want to. So that's the drawback of this architecture. So you really need to be aware of that. So for system topology, I was not able to run that on the Bede system. I don't know why exactly. I didn't get a chance to fix it. So in my system in Montpellier, I have 6 GPUs, and what we see, can I annotate? Yeah. What we see is that we have, so here, 3 GPUs. Here, in your case, it's 2, but they are interconnected with NVLink. That's the first thing. On the other side, we have 2 other GPUs who are interconnected between each other. And then one of the important stuff to see is the MLX5 adapter. So here, GPU 0, 1, 2, yeah, GPU 0 and 1, they have direct access to the MLX5 0, and these 2, GPU 3 and 4, they have direct access to MLX 5, 2, and 3. I come back later why it's important. So now we're getting GPUs. So you might already know everything about GPUs, but again, I don't really know the understanding. So I will do the quick overview, and later we can go into more details if it's required. So the purpose of GPU is not to run all application, and that's really important. What we have seen in most of case for application is that only 3-5% of the code needs to be ported into GPUs. So all the rest, mainly managing I/O, reading files, writing output files. Usually, you don't need to do anything on the GPU side. Sorry. So that's why it's important to have a fast sequential CPU to be able to run this demanding serial processing. So it's an heterogeneous architecture. You have the CPU, the GPU that are accessing different type of memory. So it's really important to understand how it works to optimize the application efficiently. So from a compiler view, you have the P9 with fat cores. So about 128 threads available on your system, 32 cores. And on the other side, you have highly parallel cores, about 248 per GPUs, per SMs, and there are about 80 SMs per GPUs. So that makes a lot of hardware threads to use. Again, GPU architecture, it's composed of 80 simultaneous, I forgot the name of SM, whatever. So it's, let's say, a core. There are about 80 equivalent of core on the GPU, and each GPU, I missed this one. Each GPU, each core, let's say, sorry, have a lot of compute units. So compared to a traditional processor, you see that most of the space used on the chips is used for compute units. So that's what makes the GPUs and the accelerators efficient for the compute. It's that it's only doing, let's say, dumb stuff. It's not doing I/O. It's not doing anything. It's only computing. And just a simple word about the tensor cores. So it's something that has been added in the V100 system. It's a specific compute units, hardware compute units that allows to compute more efficiently the tensor operation. So that's what makes the V100 especially good for AI. So everything I said about the V100 is the same for the current generation, let's say, of GPUs. So the A100s have exactly the same architecture, only a little bit more bandwidth on the HBM side. And I think there is some additional SMs available, but grossly you have the same architecture on the V100 and A100. Now regarding on the network, I said there is a specificity on the system. We have a single PCI Gen 4 by 16 to put the network card. So by 16 means that you can get more than 200 gigabit of speed between on the card, and we divide 8 lanes that are directed to CPU 0 and 8 lanes that are directed to CPU 1. So it makes a direct connection between for each CPU. So you don't need to run anything on the crossbar. So that's why it's not a big issue to have only 64 gigabit for the X bus. It's because you don't really need it. Yeah, and the fact to have Gen 4 by 16, we can leverage the available bandwidth of 200 gigabit, available with 2 IB EDR4X links. So the two strategies that you can work with is that configuration. Is that the traditional one is to really balance the system. So really consider one NUMA node with socket 0 and its 2 GPUs, and another NUMA node with a Power9 socket 1 and its 2 GPUs, and they can both be assigned a specific IB path, let's say, to get full bandwidth available. So that's usually the strategy that we adopt. So the balance strategy. So you dedicate one IB link per socket. So here for socket 0, you would use this path. And for socket 1, you would use this path. So it means that here communication will go directly there, and here it will go directly there. So that's the first strategy. And if your application is really network bandwidth bound, the other strategy is to use both this path to go to the network and also to use this path. So in that case, you leverage all available bandwidth. So you don't get 2 times the bandwidth, but you get from the measurement we made about 80% efficiency of the aggregation of the tooling. So if you have some applications that are very network bandwidth bound, it might be an option to use that. But the key thing is really to understand that you have 2 interfaces that are actually referring to the same port. So it's important to understand that you can you can have some issues with default query from the underlying libraries that can't know exactly this topology. So since it's specific only to this system, there have been no implementation outside of Spectrum MPI that covers this specific stuff. So unfortunately, it's something that needs to be understood so you can optimize your application properly. So now quickly regarding the software. So there is two big difference that consists with Spectrum LSF and Spectrum MPI. So I'm an IBMer, so I would always say it's unfortunate. It's unfortunate because a lot of optimization has been put in LSF and MPI to leverage this system. So a lot of work to integrate GPU efficiently, and in addition, a lot of work to integrate the specificity of AC922. But as I always say, it's always possible to tweak the open source software to do a little bit better than it's doing by default, because you know what you want to do later. Another difference is GPFS versus Lustre, but in Pangea total cluster, we are also running Lustre, so there is no issue with that. It's only, let's say, 5 system. And the other stack, you have the proper tool. So one key difference also with the Power9 system, so I don't recall the exact number. I didn't check for this latest Skylake, but what I recall is when we introduced the Little Indian instruction, we moved from 600 instruction on the Power ISA to something like 900, because some of the compute stuff must have been doubled. But when we compare with x86, the x86 CPU is about 2000 instruction. So the CPU, the x86 CPU is a lot more complex. So that's why you would use MKL. But in case of Power9, it's simple to use. So traditionally, all open source compiler and libraries are able to produce efficient code for Power. It's here. So ESSL is better, but I know that it's difficult to use, and OpenBLAS is doing a very good job. Again, it's thanks to the simplicity of the instruction set. You have no trouble using this kind of library.
Sorry, Ludo, I think there's a question in the chat about, did you say only Spectrum MPI understands the IB Neumann node affinity?
Yes, especially since OpenMPI, so I didn't mention, but it's OpenMPI 4, and it's relying on UCX. We'll come back to it. Difficult, sorry. It's a lot better than my handwriting. So it's UCX is doing. There is no a new layer between the MPI and the hardware, and everyone is moving to UCX because it's easier to change only this component to optimize communication. But what's happening is that the UCX component is external to OpenMPI, so you don't. There are limited options to instruct what you want to do with UCX, at least at the moment. I think it will change, but at the moment, since the purpose is to get rid of the transport layer and leave it to UCX, there are limited options to do any optimization. I will try to open the chat. Yeah. So there is still, and we will see it, UCX understands the affinity of the adapters. It's based on the NUMA NUMA CTL, not NUMA CTL, NUMA library that understands the system topology. The issue, if we come back here, is that the NUMA HWLOC-LS does not make any difference. It does not know that MLX5_0 and MLX5_2 are actually the same port. So at the end, you won't be able to leverage the interface because it does not, it can't know this information. Well, it could, but it would take too much work. So it would need to query the ID and to figure out that it's the same. So it's something that the automatic discovery tool can't figure out for now. But we'll see the optimization we can do. Yeah. So then for the OpenACC, so for the software stack, we come back to it, but very quickly as an introduction, there are mainly three ways to optimize applications. So 4 with external libraries. But if you want to change your code, you have 3 possibilities. So OpenACC, so it's supported with PGI, no, sorry, date. You can use it with yeah, PGI, sorry, it's here, and GCC. So since GCC 8 for Power, you can have support for OpenACC. So it's the first option. The second option in the middle, let's say, is to use CUDA directly. It's a little bit less portable, but a little bit less readable. But it's yeah, that's an option. That's something that we don't advise, especially now that the 2 directive standards are working well. And the other standard that you can use is OpenMP, so OpenMP 4, 4.0 and 4.5, and soon OpenMP 5. So this OpenMP is supported in XL compiler and also LLVM that is starting to take a good place versus GCC for everything. So most of the compiler, Intel, XL, and PGI, for instance, they're using the LLVM backend. So that's something that that is coming for almost everyone. So that's the 3 possibilities you have to optimize your application. So after that, it's something that must be decided when you start porting your application, what model you want to use. And there are always, as we'll see, questions you need first to ask before doing anything. Sorry. So some example are on your system. So the Infiniband device, because I really think it's important. You will see the NUMA node 0, which is the first CPU, and the NUMA node 8, which is the second CPU. I forgot to mention that, but the power chip is meant to go up to 16 sockets per system. And by default, if there are 2 CPU, it will be number 0 and 8. So that's also something important to note when you do binding. So it will be membind 8 and membind 0, yeah, versus 0 and 1 on x86. And again, you see the Infiniband device. So you think you have 4 devices, but actually you have only 2 links. So you need to optimize the use of these 2 links. So with UCX, we have experienced that in Chineka, especially, but in a lesser extent because they have only one port IB link, so it makes things easier to configure. And you think UCX is doing the right decision. But when we want, if you want to see exactly what you are using as Infiniband device, the only option is to recompile the UCX library and enable logging. So it will allow to then export UCX log level to info, and it will tell you what device you are using. Unfortunately, we have not been able to do any study yet if enabling this logging option would harm the performance. So I can't tell if this is something that is advisable to do for production library or if this is something to do only for development libraries. But anyway, it's easy to reconfigure, and yeah, you can do that on your site. So when I made a first test with one process per GPUs, it was unfortunate to see that the UCX server was using MX5_1 and _3, which correspond to the same physical link actually. So it means that instead of using 200 gigabits per second of bandwidth, I'm only using 100. So I have a quick script here that tries to simulate what has been implemented in Spectrum MPI. So always good to reuse what intelligent guys have been doing. So it's with the Spectrum MPI, there are 2 variables, PAMI IBV device name and IBV device name _1, that represents that allows to pinpoint the device that will be used either by socket 0 and socket 1. So if the second one, the _1 is not specified, everyone will use the first variable. But here the purpose is really to use specific device. So the purpose of the script is only to identify where I am bound, and when I know where I'm running, I can specify which UCX device I will be using. And sorry, there is something missing in the script. I try to edit it later. And then you run your script, you call your application $@ to $@ to run your application. So when you do that, so you, instead of only running MPI run your application, you do MPI run your script, and then you see that you will have proper binding. So the two CPUs that are, the 2 processes that are running on the first CPU will use the _0 device, and the 2 CPU running on socket 1 will use the _3 device. So it will run on, I should have put back the thing. It will really use the 2 paths that we want, that are this one and this one. Sorry, this one. So it won't overlap, and you will have direct dedicated bandwidth for each socket. Sorry, I have to clear. So that's really one of the first key thing to know about this system. The second important part, so question is, can that be fixed? Can that fix be done automatically for less technical users? Yes, this is a discussion that we are having with Mark, if I recall correctly. Typically, Bede MPI run is doing already a lot of stuff. So technically, it wouldn't take too much to, instead of directly calling the application, to also run a binding script that would do that. So that's something that that might be done. So again, it's something that is integrated by default on the, let's say, vendor product. And since you are using open source, it's something that must be implemented on top of the default behavior of the application. But yeah, definitely this is something that can be added. Typically for Chineka, that's something I've been provided to some users. So now we're getting GPUs, and there will be a similar question and the same answer. Yes, it can be done automatically. So there are three modes for the GPU. The default mode is that you can run multiple process on the same GPU. But there is a big issue with doing that is that you have a lot, the context switching for GPUs are really, really expensive. So that's something that you usually don't want to do. But still, sometimes the application does not care, does not use fully a GPU because using ATSMs can be hard sometimes. So it might be good to use two process per GPU or more. In your configuration, up to 8 might be a good idea. But if you do that blindly, you will see that you have a drop in performance as soon as you put more GPU into stuff. But that's something that can be fixed, and we'll see how later. So what we advise everyone to do, and again, this is something that in LSF can be managed. It's to use the GPU as exclusive process to avoid any drop in performance when you run multiple process per GPU. And prohibited, that's a mode that you don't want to use. And in case you want to run multiple process per GPU, there is a new facility in the V100. It's called CUDA multiprocess service. So it's not new to V100. It's not new to V100. It's new. What is new with V100 is the hardware support. I have to find the annotate. What is new with V100 is the hardware support. So previously in P100 Pascal generation, you still have a CPU process that runs on the CPU, and each context is managed by the CPU. So you have high CPU utilization, and you have the context switching is still a little bit expensive. But with Volta, you have a dedicated space on the hardware that allow to backs up, I think it's up to 32 contexts. And when you run multiple applications, you don't see any drop in performance. And the CPU process now is only there to control the access, but there is absolutely no performance related concern with the CPU process. So first, it won't use CPU cycle or very little. And then on the CPU side, you will have a lot of you will have better performance. So at one point, we even decided to put the default to start MPS directly on our benchmark system. So because we haven't seen any drawback in performance. There's only one application that causes us just trouble because it was doing hard-coded stuff with the CUDA visible devices, but otherwise there is absolutely no differences. So question is about the GRS complement exclusive process. From the test I've made, I haven't seen it working. But again, I'm not a big expert in Slurm. The big next step is not is to be able to start the MPS automatically. That would allow you to get full power of the V100 because you would be able to put more workload in there. To clear. So again, we have built an helper script. So again, this is something that we built since 2014 when LSF and Spectrum MPI were not that good in binding, using proper automation and so on. And that's something that we later shared with the LSF team so they could include that in the product. I think now Slurm is able to do the same thing, but it's all a matter of configuration. So here, it's something that you can do as a user. You will start MPS. So if you start MPS as a user, you will be the only one able to use this MPS process. This is the only drawback to use it as a user. But usually on an HPC system, when you book a GPU or a node, you are dedicated. So you especially don't want anyone else to use the GPU. So it's not a big concern to use it as user. The other drawback in using this MPS script we have seen, and again, I don't know how Slurm is configured on your side, but sometime we have seen that there are ghosts MPS daemon that are running because the job failed and it did not stop. It did not reach the end of the script to stop MPS. So that's something that again can be used to check if it's worth to use MPS and to overload GPUs with multiple tasks. That's the first step as a discovery process on how to best run an application. And later, it should be discussed with what is the best implementation in terms of production with the administrator of the clusters.